Hi, my name is Jonathan Brophy. This is joint work with my advisor, Daniel Loud, at the University of Oregon on instance-based uncertainty estimation for gradient-boosted regression trees. Now, the goal of this work is to accurately model the prediction uncertainty for different gradient-boosted regression tree models. Now, GBRTs are hugely popular for solving regression problems, especially when the data is tabular. However, these models provide no uncertainty of their predictions, only providing a scalar output. But prediction uncertainty is important for certain domains such as weather forecasting, finance, healthcare, etc. And quantifying the uncertainty of different predictions can increase the interpretability of those predictions. In this work, we're talking about GBRTs, solving the task of probabilistic regression, in which the goal is to estimate the probability of y given some input vector x. Previous approaches to solving this problem include a multi-parameter boosting approach called NGBoost, in which they train an ensemble for each parameter in a parametric distribution. More recently, Springers et al. Introduced PGBM, in which they take a leaf value modeling approach, where they estimate the uncertainty of each leaf value and update the probabilistic prediction of x as it traverses through the ensemble. Our approach, which we call IBUG, uses instance-based learning, where we identify the k training examples that appear in the same leaf as x most frequently throughout the ensemble. And then we use those examples to model the posterior. So for example, to model the output as a normal distribution, we use the scalar output of the GBRT to model the mean, and then we use the k highest affinity training examples to estimate the variance of that prediction. When comparing IBUG to NGBoost and PGBM on 22 benchmark regression datasets and assuming the output follows a normal distribution, we find that IBUG wins 17 and 13 times respectively, while losing only 2 and 3 times. These results are statistically significant over 20 random folds. On point performance, IBUG slightly outperforms PGBM. However, PGBM and IBUG significantly outperform NGBoost, since NGBoost is optimized for probabilistic, not point performance. Overall, IBUG provides competitive point and probabilistic predictions. IBUG is agnostic to GBRT type, and using different base models can improve probabilistic predictions. For all of our experiments, we use LightGBM as a base model for IBUG. However, we've also experimented with using XGBoost and CapBoost, and on some datasets, this can lead to improved probabilistic performance. One of the unique advantages of IBUG is its ability to model both parametric and non-parametric density estimators, since IBUG uses empirical samples to model the posterior. And we see here on the MEPS and WINE datasets that using a parametric Weibull distribution and a non-parametric KDE density estimator leads to significantly improved probabilistic performance than assuming normality. Since IBUG uses instance-based learning, inference can be relatively slow due to the computation of the affinity vector over all trees in the ensemble. However, IBUG can approximate the affinity vector by sampling trees uniformly at random. And this can significantly increase prediction efficiency, often by 1 to 2 orders of magnitude, while maintaining competitive probabilistic performance. So by sampling trees, IBUG can trade off between prediction efficiency and accuracy. If you'd like to know more, or if you'd like to start using IBUG today, links to our paper and our publicly available code are down in the bottom right. Thank you very much.